Happenstance is a hell of a thing. Our individual realities often have happenstance that would define whole epochs of our life. Sometimes, though, for some of us, rarer still one of us, there's a happenstance that completely alters the course of our species. Our collective scientific history is full of such individuals, and such lauded happenstance. We're told about the giants of science, who so altered time by their revolutionary ideas. Einstein, Curie, Newton, Darwin, Tesla, Lucretius. Though somewhere very recently, we seem to have either run out of steam and no longer produce such people, or they stopped reaching notoriety during their lifetime. Something I was introduced to in the startup world, but now I realize is a truism everywhere, is that you can have the best idea, execute it perfectly, but come against some wrong timing and end up falling flat on your face. In the consumer world, it's quite easy for the face plant to be measured. Did people buy it? But what about in science, where there's supposed to be a methodology that can be reproduced to express the same results? But what if you reproduce the experiments, only to get different results? Kevin Simler and Robin Hanson wrote a book titled The Elephant in the Brain, which tries to introduce and explain a fundamental part of human beings, that just like the elephant in the room is massive, takes up much space, but we refuse to acknowledge it. According to them, the elephant in our brains is that deception and self-deceptions are key aspects in the way we function, and furthermore, what motivates our deception is to be an accepted member of a community. That aspect of ourselves is only one of the many roots to the base societies that emerged with us. And as far as I see it, if we don't recognize that about ourselves, we can never transcend past it. Nor will we be able to stop systems we create from mirroring that aspect. A common phrase, where there's people, there's politics. And outside of the lovely alliteration there, it's a great truism for what starts to occur when we start to group together. Why I choose to spend so much time on this show talking about politics, trying other ways to see it, whether it's ancient history or science in this one, is because I'm trying to better understand the fundamentals, the basics of who we are and the reality we're in. In this interview, beyond trying to capture a truly mind-bending reality about the world we live in, it gives us a glimpse into the elephant in the brain stuck at the center of our scientific community. One of the ideas being we know all there is to know about water, how it forms on our planet, how it's used in our cells, through onto how it can combine and what will result from that. Though those are the norms my guest Dr. Gerald Pollack has upended with the help of his team, in the discovery of an additional phase of water. Turns out if you're curious, get the right timing, read Happenstance, and have the courage not to be affected by others in your community trying to push you out and discourage your ideas, you can discover all that we do not know about water. This was an incredible moment for me to be able to talk with Dr. Pollack. I'm very grateful that he took the time out of his busy schedule to do so. And in listening, I hope you walk away more curious about the world around you. The first part of the interview with Dr. Pollack, he tells me what makes him most happy, which leads rather fittingly into a sneak peek behind the curtain into how the highest levels of science is done. Before we go into what is structured water, how does it behave, and what does it teach us about the world, then wrapping up talking about the health properties of structured water and some of the amazing research being done, to say nothing of the paradigm-shifting engineering potential that can be done. Dr. Pollack has an excellent website that has all kinds of links to his work, including the book that's sitting at my coffee table, which explains this discovery, titled The Fourth Phase of Water, Beyond Solid, Liquid, Vapor. If you do find yourself on his site, I really encourage you to head over to the Publications tab and check out Dr. Pollack's essay, that the title being true to his character is A Few Potentially Helpful Guidelines for Impactful Writing. I've taken writing seriously pretty much all my life. I can tell you it is a wellspring of wisdom, and should be considered required reading for anyone looking to write something worth reading, from an email, love letter, or an intro message to a podcast. He also has 2 more books that are close to ready for publication, which he mentions on the call, and I can tell you I'm absolutely itching to read them. Quick note I want to make before the episode, and any potential deep dive may occur. Dr. Pollack is not affiliated with any of the many products you're likely to find along the way, which steal his picture off his site and cite his work. Just like you may have heard me mention in regards to emerging tech in the episode prior even, there's a lot of grifters out there when there's a new discovery or technology. All right, with that, thank you immensely for Dr. Pollack for taking the time. Thank you to the listener, who I'm wishing well wherever it is this finds you on our lovely blue planet. Real quick before the episode begins, if you like what you hear, please tap that follow or subscribe button. You also can find this episode, all episodes in the series, or check out our Daily Minute podcast by visiting us at bandwidth.productions. All right. Well, thank you very much. Again, I really appreciate you taking the time. Would you kick us off by introducing yourself really quick?
Sure. I'm Gerald Pollack, and I'm not sure what to say. I'm a professor at the University of Washington in Seattle, and during the past couple of decades, we've been studying water, and water is my passion. I've got a lot of other passions, but uh, yeah, we discovered something new. I mean, what we discovered is not new, but the discovery is new. We found that water has not the 3 phases that we all learned about, solid, liquid, and vapor, but we found the 4th phase. And the 4th phase is not it's not merely a kind of laboratory curiosity that comes from the recesses of some reclusive scientist's laboratory, but it's something something that is a phase of water we discover that's all over, and it's water that fills our bodies. It fills all our cells, and I know that a lot of you may be skeptical at first of something like that, but we all think that our bodies are filled with water. We know that our bodies are 2/3 water, and we think of the water that's in our cells as liquid water. And the way you can easily dispel that notion is really simple: cut yourself. Now, if your body is filled with liquid water, as soon as you cut yourself, the water should come pouring out, like a water pipe that's fractured. That doesn't happen. At least it doesn't happen to most of us. Maybe we get a little blood coming out or a lot of blood coming out, but we don't get water that's pouring out. So the water that's inside our body is different from what we all have come to think. And what it is this 4th phase water that we were able to identify, which has a kind of gel-like character, and it sticks to the solids that is inside of our body. And that's why when you cut yourself, it doesn't come pouring out. So this is simply by way of introduction. And I just wanted to begin by suggesting that this kind of water is not ordinary water, and it's this so-called 4th phase water that we identified. Is that an okay introduction?
Oh, you knocked it out of the park. That's more than okay. Yeah, and I'm really geeked to get into talking this about you, especially because how much of a shock it was to me to first understand that your discovery was out there. And I want to get into that. But first, there's a question I ask every guest when they first join to kind of understand ourselves before we get into the topic. And what I want to ask you is, what do you like to do that makes you happy?
I like to discover the workings of nature. That is what makes me the happiest. I'm happy to expound on that if you like, but
Of course.
you know, uh, okay, I will say a few words. So I started my career studying muscles and how muscles contract, and I was highly skeptical of the theory that was put out there, and it was put out by a Nobel laureate who was, you might say, a Nobel laureate among Nobel laureates. His name was Sir Andrew Huxley, and because he comes from the famous Huxley family, everybody thought, well, this is a godlike figure, and therefore he must be correct. And the problem is that he didn't agree with the evidence. Rather fundamental evidence was simply out of accord with the theory. And in my own naive way, I looked in. We did many experiments, and the results of the experiments simply didn't agree with the predictions of the theory. They were way out of accord. And in, as I say, in my own naive way, we pursued experiments for quite a few years, every one of which produced results that were grossly out of accord. Having spent quite a few years doing that and having come up with a mechanism that I thought was closer to the truth, and I wrote a book about it in 1990, some time ago. I After a while, it's not that I gave up because I thought that the ideas that I expressed were closer to the truth than what had been presented. But I came to the realization that the process of science is not a process that leads to a real understanding of nature. And it's highly political. And let me explain. It's political because just think about it. You have a Nobel laureate among Nobel laureates on one side, and on the other side you have this guy, with a white beard and whatever. It was not white at the time, saying, "Hey, it just doesn't work. It's not right." And now, if you're in the field and you have to decide which way are you going to lean or bend, it's a no-brainer. You're going to follow the Nobel laureate because that's the way to go. You get anointed by a guy named Huxley, and wow, that's great for your career. And so it just simply doesn't work. The challenger has almost no chance of success. That's not why I changed fields in the field of water, but it is a factor that I think that pervades science nowadays. That it's really difficult for the scientist who is genuinely in search of truth to get there. There are too many obstacles along the way, and the obstacles, it's a little bit akin to the political situation. You know, if you want to get elected, depending on who your constituency is, you stand for, not necessarily stand for truth. You stand for whoever will get you elected, and it's kind of similar in some ways in the scientific system, and that's why if you were to ask yourself, here's a question for you or anybody in your audience, it's a challenge. Okay, so I ask you to name even a single scientific revolution that's occurred in, let's say, the past 30 years. I don't mean a technological revolution, like an iWatch or an iPhone or the Zoom that we often use. I mean a fundamental scientific discovery that has already succeeded in changing the world. Examples from a long time ago, 60, 70 years ago, the genetic code, that's changed the world, for the better or the worse. And maybe 10 years before that is the splitting of the atom, again, for the better or worse, but it was a scientific revolution. Whoever thought that the atom could be split? Those are genuine scientific revolutions. Now, the challenge I would ask you or anybody to name one during the past 30 years that has succeeded, not promised, but succeeded in changing the world, and changing everybody's life. I've asked that question numerous times, and I get a blank stare. What are you talking about? And head scratching, and some people will say, "Oh yeah, the Higgs boson." Well, has the Higgs boson changed your life in a meaningful way? It sounds like like a modern dance or something like that. The Higgs boson, uh, it hasn't succeeded, and this is an indictment of the process of doing science, because in the past 100 years ago, when there was virtually no money that was put into science, we had revolutions coming practically every year, especially in the field of physics. With Niels Bohr and Einstein and Schrödinger and all of those physicists. But now, you ask the question now, and it's you can't really think of anything that's like that, which is really a pity. But and it has to do with the process, I think, of doing science. So maybe I'm going astray in trying to answer your question, but I've come to realize now, having been in several fields, that it's the same in every field. There's money. Scientists complain there's not enough money, and perhaps they're right. But the money is not spent in a way that allows for scientific breakthroughs. It's kind of programmed. If you try to get money to do research, and you need money to do research to run a laboratory, and you go, say, to the National Science Foundation or the National Institutes of Health, depending on what you're doing, they program the different areas that are allowable areas of research. They'll say, okay, we're interested in the genetics of cancer, and if you have a proposal, send it in. But if you're dealing with cancer in a way that doesn't deal with genetics but deals with another approach, you don't have a chance, because the reviewers are the people who are into the genetics of cancer. And if you propose something that's wildly different, in order for them to make judgment, they have to educate themselves in your field, and they have to convince all the people sitting around the review table that your proposal makes sense. It's a real challenge. And of course, the other people sitting around the review table will ask that particular reviewer questions, and the reviewer has to be able to answer the questions. Otherwise, the reviewer himself or herself is demolished. Nobody wants to be in that situation, so it's easier to say, oh, well, this is pretty interesting, but they haven't proposed the right kind of statistics to analyze this, and therefore, well, it gets a score that's below the funding threshold. And people know that. They understand. Scientists know that. And any scientist who has interest in success simply will not propose a radical idea. So what that means is that the radical ideas that have some chance of success and some chance of changing the world in a really major way, they can't get started. And this is an indictment of the system. And nobody in the system really wants that kind of outcome. But the system itself has so much inertia that it's difficult to change. And so scientists are discouraged from coming forth honestly with what they believe. And what they do instead is to propose something that they think will be funded. You see, that's the goal. That's the aim, to get funded. Because you can't get funded, you have nothing, and you lose, and you get fired from your university position because they have interest in money. They get overhead from these organizations, and they live on that overhead. And if you don't get your money, then you're out. So the system itself is designed in such a way as to make revolutionary progress almost impossible. And that's why we haven't seen scientific revolutions in the past 30, 40 years. And it's, unfortunately, it's not sure how to put it in a polite way, but it's
You don't need to
stymied.
be polite.
It
Yeah.
is stymieing the process of science. Now I'm not sure how I got off in that direction. We were
I
beginning
think
to
you
talk about water, but
I think you answered what
um,
makes you happy by also expressing what makes you very unhappy, so that by beating the system in some way, perhaps you get a new
yeah,
stage of
right,
happiness.
right. So
Yeah.
I yeah I will just complete the thought. It's easy to go astray by saying that what makes me happy is discovering what I think is scientific truth. And I think we may have done that in the field of water. And I have two books that are very close to being published on different subjects. They're awaiting publication. I'm waiting for my son, who's my artist, who's a very gifted artist, and he's busy remodeling his home. So I'm waiting for him to finish the illustration so the books can be published. They're just about at the threshold of publication. And they deal with other aspects of nature. And again, it's nature that I think I perhaps have some idea of the real explanations, not the explanations that exist right now. And the next book, for example, deals with an assortment of subjects whose bottom line is that electrical charge is really responsible for governing many phenomena that we see every day, but we think we sort of understand. But if you dig below the surface and ask the secondary question, there's no answer. And so the kind of satisfaction that I get from that is huge. I have no idea what the world will think about. Well, I do have some idea because I've subjected the ideas to the criticism of my colleagues, and there is plenty of criticism. I deal with subjects like um, where should I? What creates wind? What turns the earth so we see day and night? Um, how does weather actually occur? It's surprising how little is known about about clouds and rain and like what keeps the clouds up in the sky. Clouds are made of water, and if you were to climb a tall ladder up to the level of the clouds with a pail of water and turn it over, the water would come right down, right? Well, the cloud's made of water. How come the cloud doesn't come right down? Or sometimes it does. It comes down as rain. But wait a second. Why does rain come one droplet at a time instead of one bathtub dump? Those are questions that people don't ordinarily think about. But if you really want to understand nature, you need to be able to understand that. And I can't tell you what great pleasure I have, my favorite activity, working on those books. And another one, maybe I'm going on too much, about the structure of the atom. Um, this is pretty fundamental, and we all we all learn about the structure of the atom, but we never think twice about it because it's been around. It's been around for 100 years or more. Niels Bohr one day had an idea that the atom might have the same structure as the solar system, right? And cool idea, and it makes sense because nature tends to repeat itself in different forms in different ways, and so it makes sense. So you have a nucleus that's sort of equivalent to the sun, and then you have electrons, now electron clouds, that revolve around the nucleus. And we all learn it in middle school, and we all think, well, it's been around for how many generations, therefore it must be correct. But if you realize that what's happened over the years is that the quantum mechanics people have gotten into the field, and and you're smiling. I'm not sure why you're smiling, but yeah. So quantum
Because
mechanics is
I have gripes against. I think quantum mechanics is one of the examples of the groupthink that you've been describing earlier. That's why I'm laughing.
well, yeah. I mean, I'm with you on on that. So they've invented how many subatomic particles, which they need in order to make that model work. You see, Good theory doesn't require band-aids, and supplements. Usually a good theory is one that explains more than you originally thought, because there's truth to it. But if you have a model that requires every year a new subatomic particle to hold together, yeah, I guess groupthink is a good expression for it. So I mean, philosophically, that doesn't work. But there are such simple observations that just don't work, and I'm kind of surprised that people have not thought about them, or at least they have not published them in any detail. And if you just think about it, the nucleus contains neutrons and protons. So neutrons are neutral, right? But protons are positively charged, and they're all packed really tightly together. And each proton has a positive charge. So when you pack together positive charges, all they want to do is escape from one another, right? They repel.
Oh, this is the Feynman like likes like.
I'm sorry, the famous what?
This is Richard Feynman's like. No, this is Richard Feynman's like likes like.
No,
Right? Isn't
well,
this what I was
well,
actually going to ask you
it,
about something along this.
well, I will. I'm happy to respond to that particular question, but there is, in order for this likes to happen, you need opposite charges in between, but there's no opposite charges in between. You see, so the nucleus basically wants to explode, and the physicists have recognized this problem, and in order to circumvent this obvious issue, they invented something called the strong force. And the strong force is a force that has exactly the right properties to hold the nucleus together in spite of that huge repulsive force. But nobody has independent evidence for the existence of a strong force. It's like a band-aid designed to cover a gaping wound. It's, um, and if someone were to ask you um, to design or come up forth with a model of the atom, and you were asked to do that today, probably they'd say, "Well, go home and try again because it simply doesn't work. The first principles are violated." You see, and then just one more. So the nucleus is positively charged, and the electrons, or electron clouds, is now thought of, they have negative charge. So you've got positive charge right at the center, negative charge out here. And what happens when you have negative and positive? They attract each other. And so the entire atom should collapse. But if it collapses, we have no atom left. We have nothing. We have a point. You see, so these are only two of a whole bunch of fundamental issues that don't make sense. And if they don't make sense, then as scientists, it's our obligation to figure out what does make sense. You see, and that's what my second forthcoming book is about. And the original question was, what gives me pleasure? And I can tell you that that a huge pleasure comes from at least thinking that you're on the right track in figuring out how nature works. I could go on and on and on that one, but I think you probably have other questions to ask, I think.
Now I have millions more. I have millions more questions now after hearing that. I'm excited to hear that there's those two coming. I'm gonna have to follow that very closely. I'm very excited about that. One thing to say about the general state of science is sometimes I wonder if it's a product of scale. Like the institutions have been at scale now, for so long, and there hasn't been much revolutions in this time period, perhaps because the scaffolding in place is so strong to keep down dissenting opinions because of what's built on top of the existing order, and the shakeup that may come. Because Einstein, Bohr, all of them were at a time where everything was new. So, there wasn't the long-standing institutional connections and access and all of that to go. And I wonder if it's, where there's people, there's politics. And politics at scale often looks very similar, and I wonder if there's something to that.
I hear you, and I agree with you. Science has become institutionalized, and there 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 are ways to circumvent the issues that we've been talking about. And at one time I was really active in trying to implement changes in those two institutions, the National Institutes of Health and National Science Foundation. I was on various advisory boards and such, and we made some progress. We people began to understand that this was an issue, and for a year or so, things changed. There was an impact of not only my offering, but other people as well. But there were many stakeholders over there who had something similar to say, that we got to do something because there have been no revolutions. Um, and the key to the revolution is you can't have, if I challenge you, you can't be my reviewer. I mean, it sort of makes sense. It's like, the French Revolution. You go to Louis the 16th and say, hey, we have a few complaints, and well, thank you very much. Appreciate your honest criticism, but that that's it. Nothing happens. People who are in power like to retain their power, as we see ever so much today in politics. And it's really the same in scientific politics. So someone who's gained stature likes to retain that stature, and retaining this stature means that, if you think the Earth is flat, and someone comes around and challenges you and says, "Hey, no, we have evidence that it's round. We look at the satellite images, and if you fly around the Earth, you can get back to the same point." It looks like you try to get money. So what happens is that the institutions, thinking that they're being conscientious for such an important and potentially earth-shaking proposal like that, they're going to recruit the world's experts to say whether you're a crackpot or whether it makes sense. And who are those experts? So if you propose the Earth is round, you're going to face the experts who are all flat Earth people. The last thing they want to do is to be dethroned. So the setup is set up in such a way that you can't win. Even no matter how much evidence you have for a particular point of view, it's almost impossible to win. You see, and so you need to do something about that. And I actually, with the work that we have yet to talk about, I've been fortunate in attracting money from private funders who believe in truth seeking and have been supporting me generously. And so long as that continues, it works, because it lends a kind of freedom to actually pursue truth in the way that you see it. The institutional setup is different for the reasons I was describing. That you're always challenging the person who reviews you, and that doesn't work. Um, okay, I think I better stop here. I'm on my bandwagon.
No, that's
Yeah,
great. No, that was great.
yeah.
No, that was awesome though, to give a setup to, I mean, a look behind the state of science that I think most people don't see. Someone that I think you would be encouraged to check out is Eric Weinstein, because he talks about this a lot, in particular with regards to physics. And he has some very fascinating things to say about almost the exact same experience. But turning to talk about structured water, though,
Okay.
I did find it fascinating. Okay, so I never heard of this before, and I'm somebody who, as a friend of mine once put it, likes collecting people that are on the fringes but make complete sense. And because there's multiple people I've introduced him with them that he says fit that bill, which I think you're pretty much spot on with that too. So I found it from a tweet, and it was somebody I follow or something on Twitter that was the algorithm was presenting to me, where someone was essentially saying like, hey, like if you don't know about structured water, like don't take me on a date was essentially what they were saying. I don't remember the exact context. And I never heard, I was like, structured water, like what does that mean? So then I looked into it. I found your work. I went crazy on it. And then I found a lot of other people who have done, similar things with this fourth phase of water. And it was earth shattering to me for several reasons. I never heard of it. It seems foundational. It makes complete sense as far as what you're proposing. And one of the funny things I found last night, putting my thoughts together for this chat, was that the Wikipedia article on it is calling it like a marketing scam, and completely dismisses it, which I thought was fascinating. Which kind of
A
shows
marketing scam. I actually haven't seen that. That's interesting. Marketing. Okay. Marketing for what?
well, that people marketing structured water, that it improves your health and things like that, and dismisses the concept of a fourth phase altogether as like a afterthought. It's interesting. Uh, which is also funny because I read that right after reading some like rather promising results of people drinking and or giving lab animals structured water, which was fascinating. But regardless, and I went into it, and so what I would like to do is first kind of set up what it is. Which, if I was to take a stab at it, it's to give like a concept that listeners may understand or see in their life is, if you're looking at water as it's running down or running over something, and there's that glossiness to the top of it, that glossiness is actually another state. So we know that water will evaporate when you boil it, for example, the steam, that's evaporating water. We know that it's stable in a liquid form in a glass, like I'm drinking as we talk, or also that it freezes and it's ice. And we know those things. A fun thing that I always like to bring up to twist people's noodle about ice is that ice skating is actually melting the ice for pressure, which is why you're able to go on it, which now I think has something to do with the fourth phase of water that I wanted to ask you about. And what you have discovered or rediscovered, because I think you even have talked, I heard you talk about that there was somebody like around 100 years ago who proposed a gel-like state, is that glossiness on water as it's going over a stream or something like that, that sheen, that like plasticity that we kind of think of, is actually another state of water, which is a gel. That is, what is it? It's H3 instead of H2.
H3O2. Yeah.
H3O2. Yeah,
Yeah.
I wrote it on my whiteboard, I think, behind me. Yeah, so it's a different state, different structure. It looks like a crystal, and it has some special funky properties that potentially can be tapped for many different things. The water filtration. I saw a diagram on your website of filtering water without power, which makes utter sense and is fascinating. So is there any color you would like to add to that as far as a definition? There's another phase of water. It's a gel. It has a specific crystalline structure to it, and it exists at the interface
Yeah.
between water and the outside world.
Yeah. It's not just at the interface that you're talking about. This phase of water builds. Whenever you have a surface that has a certain character to it, we say hydrophilic, water loving, and most surfaces are like that. Um, what happens is that, so here, let's say, here's the surface of some material that has that characteristic, and the water is sitting next to it. And the first layer of water molecules, when it hits that surface, when it feels that surface, it undergoes a radical transformation from ordinary H2O to and H2O, water molecules are bouncing around. They're randomly oriented, bouncing around a fierce number of times per second or even per femtosecond. There's no real structure to it. And what happens is that first layer then undergoes a transformation and becomes ordered. And if you were to look in this direction, the perpendicular, along a line perpendicular to the surface, you'd see hexagons. You'd see a honeycomb kind of structure, repeating hexagons. That's the first layer. And then that first layer becomes a template for the buildup of the second layer, which serves as a template for the buildup of the third, et cetera, et cetera. So this kind of, we say, fourth phase water, there are other terms that we use for it. It builds layer by layer, and the number of layers is not trivial. It can build. We have examples in the laboratory where you can have as many, under maybe extreme circumstances, as like 1,000,000 layers. We're talking macroscopic scale. And the way we discovered it is we took some water and we put some particles in the water, and we used many kinds of particles, but initially something called microspheres, little tiny spherical particles, 1 micrometer or so in diameter, and they're all suspended in the water. And you plunk in this, let's say, gel. It was how we started. And we saw that, looking in the microscope, we saw that, so here next to the surface, I'm trying to get my hand in the image. It's not working very well, but next to the surface of that gel, we began to see that these microspheres were excluded. They were pushed out. So this region that was devoid of microspheres began to grow and grow and grow. And we found out later, as these layers grew and grew and grew, you get pushed out. And that's why we first called this exclusion zone, because it excludes. It seemed logical. And actually, it worked very well because exclusion zone, EZ, is easy to remember. And so it doesn't work in some other countries, though, because they use Z instead of Z. So it's a little bit awkward to say it's EZ to remember, but EZ to remember really works well. And I think that was maybe a kind of mistake, because it doesn't really tell you very much about the character of what's inside this EZ. And that's why we later called it fourth phase, but the two are more or less equivalent. So what happens is this phase grows, and let me just tell you a couple of characteristics that are fundamental. The first characteristic, well, it's structured, and this is the equivalent of what people once called, and still do to some extent, called structured water. And we're not the first at all to discover structure. This has been for almost 100 years espoused by the late Gilbert Ling, who spent his whole career basically suggesting that inside every one of your cells, the water is not ordinary water, but it's structured water. And also by the great Albert St. Georgi, who is considered to be the father of modern biochemistry. And he discovered vitamin C, he got a Nobel Prize, and he was involved in many different fields of science. A great hero, so creative, just really an amazing thinker and doer. So, in a sense, our work, we stand on the shoulders of giants. So we knew that there's got to be something there, and what we found is this hexagonal kind of layered structure. And we were curious, and at the time we didn't know what to expect. We stuck an electrode into that zone and another electrode far away in the water that was way beyond, and we measured the electrical potential difference. We wanted to see if there was any charge in this EZ or fourth phase. To our surprise, there was, and typically it was negatively charged. This zone, this exclusion zone, fourth phase, typically bore substantial negative charge. And then we're thinking, how could that be? Because, it starts with water, H2O, and H2O is neutral. So how do you start with water, and the water gets transformed into something that's negative? There's something missing from the logic. Or there needs to be some positive charge somewhere else. And we found the positive charge. So as the fourth phase grows, negatively charged, and protons get kicked out. So the positive charge lies beyond this zone. So you've got negative in the exclusion zone and positive outside. It's a battery. You stick 2 electrodes in, you measure an electrical potential difference. And, when you have a battery, batteries have energy. They produce energy, right? And we found by sticking 2 electrodes, one in the negative, one in the positive, you could light a light bulb. And you can get energy from this. That is energy from water. And this was for us. This was an amazing revelation because, if this stuff exists inside your body, it means that it contains energy, and it could produce energy for your body. Let alone the prospect of producing energy for any use that you can conceive of, if you can get the energy level up to some practical level. And of course, that's a challenge. So, at any rate, that's another characteristic of this fourth phase, that typically it bears negative charge. A third or fourth or whatever characteristic is, if you scratch your head and think about it, usually you can't get something for nothing, right? So if you're able to get electrical energy out of this, there must be some input energy, right? That starts it all, because you have something that gets put in and something that comes out. And so what is it? Well, we found that after several years, and several years of a lot of head scratching, that's why I'm missing some hair, that it came from the sun. We found that was light. And this was an observation made by a student, an undergraduate student who was doing what he was not supposed to be doing. You know how that goes. And the younger they are, in my experience, the more curious they are. People tend to lose their curiosity with age, or at least most do. So the student was doing the kind of experiment I just described, with the microspheres and the gel, whatever. And he noticed that on his right side there was a gooseneck lamp. So he took the lamp and he shined it on the chamber out of curiosity. And he ran into my office and called me, please take a look. And I looked and I was just amazed, because the region that received the illumination, the exclusion zone, was 3 times the size of the region that didn't receive the illumination. And so, it didn't take a genius to figure out that, well, it looks like the energy of light, photons, are responsible for building or providing the energy to build this EZ and to separate the charge that I just told you about. And of course, after that, we embarked on studies to find out which wavelengths of light were responsible. And we didn't know, so we explored wavelengths at the short end, from the ultraviolet through the visible spectrum, through infrared. And we saw ultraviolet, nothing. Visible light, almost nothing, until we got to the reds, when we saw just a little bit. And then we went to longer wavelengths, to the infrared. And there it was amazing. Just a very small amount of infrared energy would result in huge buildup of what I've been talking about. So we were able to conclude, this is not a complicated system. You start with water, under the right circumstances, the right kind of template, if you will. You provide infrared energy, and this EZ builds up. As a result, it separates charge, it creates electrical energy out of light. That's the transition that occurs. The water is a transducer. It's a transducer that transduces light energy, and perhaps other kinds, into essentially order and electrical energy. So those are the some of the more essential features of what we discovered. And maybe I should stop there and wait for your next question.
Yeah, no, I appreciate that. That was as I'm sure you're used to talking about it, that was a really great overview of everything. And really, everything that you hit on is so much of what was it blew my mind, honestly, because it was it seems so foundational, basic, essential to what is actually happening and occurring within our body, as you like expand on, but even what is just possible within the state. So What I want to ask before I really want to get into just some of the like how it is in our body and some of the things that we could do with it, the applications. But one of the things while we're on it is how much charge is there? Like you said that there's enough to, light a light bulb. You mentioned like how much water did it take to do that? And how big actually is the zone? Like, is it,
Well,
if you hit it, is it like millimeters? Like, can you,
that's a great question, and I've got to admit that uh, quantitation is not my strong suit. I did grow up in engineering where mathematics was important, but it's been a while, and so in fact, we haven't done a whole lot in the way of quantification. I will tell you that in the laboratory, the amount of energy that we get is very small. It's minuscule. And it's there, but it's small. And when I said we were able to light a light bulb, I'm not referring to an old-fashioned incandescent 100-watt light bulb. I'm referring to an LED, light-emitting diode, whose current requirements are trivial. So, the what one the principle we've demonstrated proof of principle, but we have not at all by any means demonstrated the practicality of this principle. That's the next step, and as you know, I'm sure, between a laboratory demonstration and practical use is the so-called valley of death. A lot of observations in the laboratory never make it across the valley of death. They fall into this great big abyss and remain at the bottom forever. They never make it. And it's possible that that's where this is going to wind up. I'm hopeful that it won't be the case. But referring back to the question that you asked before about what gives me the greatest pleasure, it's not the engineering development. It's the discovery of principles. So given the fact that in Seattle, where I live, the day has only 24 hours, you can't do everything. And we did actually put together a startup company. I was not in favor of it, but one of my students practically insisted. He said, "Oh, this is going to take none of your time." Well, yeah. And unfortunately, the company folded after a few years because of some internal, how shall I say, disagreement between two of the people on the board, two of the critical people. They simply couldn't agree with one another, even though they'd been friends for many years in the past. And because of that, we had great difficulty getting investment, and the company eventually folded. And we were working, that was on the back burner. We were working on another project that is not the same, but also derived from what we had found in the laboratory, and we were making progress on it. But as the technological developments require a good deal of funding and such, and we had some to start with, but eventually we ran into that problem. So it was just actually in the past month or two that the company folded, and I'm hopeful that someone will be willing to pick up these ideas and run with them. It's not us because we're interested in fundamental discoveries, and there are too many more to make yet. This is so crucial for humanity. The need for energy keeps, it's ruining the planet, and there's not too much debate about that. So if someone had interest in picking up on this, we would be happy to help in some ways, although not get deeply involved in whatever projects are necessary. It will require substantial investment, but the outcome could be, since we have proof of principle, the outcome could be amazing. We'll see.
Yeah. One of the things, like really what's rooted in that funding that you said, like these type of advancements need funding, is really they need a lot of failure in order to find success.
Often.
There needs to be, constant trial of error of scale. Like scale is what usually kills most ideas. It's like, okay, well, can you do this at scale? Can you do it repeatedly? Can you do it at a cost that's, makes it the inputs and the output. The outputs actually you can make money off the output. It's not constantly inputting more. So I definitely can understand that. And rarely is somebody who discovers something also the person that ends up bringing it to that scale. It's I do a lot of work in tech and startups, and with the truism that I always say is the people who start and make the startup successful aren't the same as the people who make it successful at scale, and they're not the same as the people who run it at scale. It takes all different types of personalities to do those.
Yeah, it's scale. That's the critical
Right.
feature, is scale. Yeah, exactly.
Right.
Scale. Yeah, you know very well. Yeah, that's true.
What and I mean, even if it's just the power that you've been able to get of lighting an LED is it's still non-trivial though, and it could potentially, once again at scale, turn out to be not something that makes all that much sense, but it could also be something that makes sense. But regardless, the principle of what you found, one of the other applications that I saw is desalination or filtering the water. Because if there's this exclusionary zone, maybe the best analogy or use of the exclusionary zone as opposed to fourth phase is that if you set up a filter in such a way where it's at that top within that exclusionary zone, the water that you're collecting is all that structured water. So it's devoid of any contaminants. Is that essentially the filtration system that you have proposed and tested?
Yeah, essentially, we can't conclude with confidence that it excludes all solutes because we haven't studied all solutes, but we've discovered enough of them. And some of the stuff that you'd really want to exclude is confirmed to be excluded. You can think of it sort of like similar to ice. Ice is structured. It's a crystal, and what we found is also a crystal. It's a liquid crystal, and crystals are pure. But in order to attain purity, any contaminants that had been in the water to begin with get ejected. You see, otherwise you wouldn't have a pure crystal. So, and that if you think about a glacier, as a glacier forms, beneath the lip of a glacier, the glacial moraine is all that stuff that has been excluded as the ice formed. And it's the same thing with fourth phase water or exclusion zone water. It excludes. And so, when you think about all the pollutants like pharmaceuticals that have been discarded and various poisons from manufacturing, at least many of them, if not most of them, I can't say all of them, but pretty much are excluded. And so all you need to do is set up a system where you capture that water. And you capture the water, and it should be essentially devoid of those contaminants. So we tend to call it a filterless filter. Of course, it doesn't have any physical filter. The filtration itself is done as a consequence of the separation, which occurs as the consequence of the sun's energy. So you don't need a filter. You just set up the geometry in such a way that you have an input which contains all the junk, and the output you collect the EZ or fourth phase water. So not only is it devoid of all the junk that you don't want, but also it has the structure to it, and the structure, as we'll get into if you ask me, has health benefits. You see, so you get it's a double whammy. You get or double positive. You not only get rid of the junk, but also you gain something from it, and that's why that was our first development. And the really exciting part for me, or more exciting part, is if you consider salt to be a contaminant, and you can get rid of the salt, then you've got a serious revolution, because we all need drinking water, and drinking water is running out. And at least in theory, you can take ocean water and put it through this filter and extract easy water from it. So not only do you get water that's healthful, but also it's devoid of contaminants, and it's practically infinite. All you need is sunlight to produce it. So it's pretty exciting, and
It is.
there's a huge, yeah, there's a future here, but it needs investment, and probably no small investment, because there's still a lot of fundamental science that needs to be done. um, to how should I say, um, 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 to clarify some aspects that are uncertain. And only when these aspects have been properly clarified, then you can move to the technological development. And we're actually eager to do those studies, but again, they require investment, they require money, they require someone who believes in it to be willing to invest in the fundamental science um, that underlies the potential for development. The reward is potentially enormous, and that keeps me excited.
Yeah, yeah. It's fascinating. Um, and yeah, everything about it is foundationally different. It's almost like understanding that. Well, there's a great analogy I bring up a lot by David Foster Wallace, where it's there are two young fish swimming along, and an older fish passes them and says, "Morning, folks. How's the water?" and keeps swimming along. And then two young fish turn to each other and they say, "What the fuck is water?" It's almost
Yeah.
fundamentally the same thing as learning that we live within air before knowing it and mastering airplanes and things like that and understanding the chemical composition of the world we live in because it is something so ubiquitous we don't think about even the fact that we have to breathe in order to stay alive. Your discovery of that is very much akin to that.
Yeah, the last one to notice the water is the fish, right around them. Absolutely.
Right. Yeah, exactly.
Yeah.
Yeah, exactly. Exactly. Um, I want to ask about the health properties, but there was one thing that sparked in me when you were saying that. So I live in the Midwest, and I know quite a bit about glaciers because I'm into geography, and the glaciers are huge in the story of the Midwest. And one of the things is that the glaciers did carry, and they did have rocks and stuff within them when they got dropped. Like in my yard, actually, I have some massive boulders that are, there's a term for it, archaic, that have been here for a long time, and they're huge. Um, you know, what is there anything that you've discovered yet that's locked within that area? Is that such a thing, or is the properties of it itself and the crystal structure and how it forms truly exclude everything, or is that something that is that some more of the science before you can get to the engineering that has to be figured out?
Yeah, well, yeah. So I oversimplified. So when you have ice, you have domains of ice. So there's one domain that would be a pure crystal, and there's another domain next to it whose orientation may be a different orientation. Um, you see, and in between is water actually between those domains of ice. And so that water can actually contain all kinds of stuff, but the ice crystal itself, the particular domain, is essentially free of contaminants. So if that answers your question,
It does because there's like it's like super cooled water or something like that. It's like water that's actually colder than freezing, but refuses to be able to have because of pressure can't actually freeze into a crystal. If I remember that physics properly
well,
enough.
water, it's a misnomer. Water doesn't always freeze at 0 degrees. It actually melts at 0 degrees, but there are reports in the literature of under certain conditions, water won't freeze until you bring the temperature down to as low as minus 80 degrees C.
Wow.
I mean, this is enormously colder than what you might think. So it depends on conditions. The if you have a glass of water and you gradually reduce the temperature, yeah, it'll freeze at roughly 0 degrees C. But depending on the conditions, it can be radically different from 0 degrees. So we learn about 0 degrees or 32 degrees Fahrenheit, but that's certainly not always the case.
Wow.
So when you could call it supercooled or whatever, but you could also say that there is no absolute freezing temperature.
Yeah,
It's equivalent.
that's interesting. Everything is relative, including the freezing of ice.
Right.
Uh, are you familiar with Schrodinger's lecture "What Is Life"? And I think he gave it in like 1945 or 44. The date is interesting to me because I feel like part of the reason it got
I think he
lost.
wrote a book on that, and yeah, but I can't remember the details. I'm sorry, but please expound.
No, it's quite all right. It's only there's only yeah, there's only one part of it that I want to bring up. First off, it's fascinating because there's a lecture that I think there was a book that he published, but the lecture I find best because he goes off the cuff a little bit in the beginning, saying like, scientists are usually not supposed to talk about things outside their field, but I'm going to put that on the
Yeah.
side and talk about things outside my field. And he talks about, what is life? And part of it, I have this obsession with fractal geometry and most recently, like the science of scaling, which is very related to fractal geometry, actually. So when he was talking about this part, it really stuck with me and has been something that I've been thinking about a lot. And then got sparked with a lot of the things that you were talking about, especially some of the health benefits. But he talks about, what is life? And in the analogy he actually uses to talk about what it is he uses crystals. And he says it's almost, how crystals form, how they come, and then the structures that they take and what they look like and all of that. Life emerging, he posits should be something that we almost see more as a crystal, which I thought is an interesting segue into just saying like, what are some of the benefits of taking this structured water, crystalline water, and actually consuming it? Because the beginning part where you said you cut yourself, you're not pouring out water. It's not like we're just a bladder of water. We're actually, almost coated with this structure, this crystal over every fiber of everything. So how is that affecting, and first, I guess, how is it composed inside of us? And then by proxy of that, how is increasing the amount of that by drinking it or consuming it affecting us?
Yeah, that's a good question. It's a broad question. So let me let me begin just to introduce. If you read a textbook on either cell biology or biochemistry or anything like that, you'll learn that water has essentially no role. It's two-thirds of us. And by the way, if you that's two-thirds by volume. If you actually take the molecules and line them up, all the molecules in your cell or in your body, and line them up one by one and do a count, more than 99 out of 100 are water molecules. Because they're small, to make up that two-thirds volume, you need a lot of them. And someone has done the arithmetic, and it's more than 99 out of 100. It shocks most people to hear that. But what's even more shocking is the current view that 99 out of 100 molecules in your body don't do anything. It's like it's like a bathtub that bathes you. The water around you doesn't do anything. You're just sitting in it. It's the same thing with the so-called
Makes you
important
pruny.
molecules of life. They don't do anything. They just happen to be there. Well, I don't know who came up with that idea to begin with, but it sounds to me anyway to somewhat unreasonable to think that 99 out of 100 molecules are just there. They don't do very much. You might say maybe even almost arrogant to come to that point. Well, I wrote a book in 2001 called Cells, Gels, and the Engines of Life. And it wasn't nearly as popular as the later book called The Fourth Phase of Water, which you're maybe familiar with. Um, but what it brought forth is evidence that water plays an absolutely central role in every important process that the body participates in. From like muscle cells that contract, secretory cells that secrete, um, nerve cells that communicate. Water in each one of those cases and more is central to whatever process goes on. The water is not irrelevant. It's not just a background carrier of the more important molecules of life. The water is central to everything that goes on. Now, this is not a popular view, and it's not the view that you'll find in any textbook. But if you look at the evidence, I think it's pretty clear. So the water is important. Now, as I suggested to you, the water that's inside your cells is fourth phase water. Um, So if that's true, if the water inside your cell is fourth phase water, and water really counts, it means that if your cell is not filled properly with fourth phase water, your cell is not working very well. So for example, take the muscle cell. Um, it needs to be filled with this water because the water is central to what happens when your muscle contracts. And if you don't have enough of this water, the contraction is your cell is going to be dysfunctional in some way or even pathological. So your challenge then is to refill the cell with this kind of water to so that there's a full complement of easy water. And if you don't have enough, you would call it so-called dehydrated. I know I suffer myself from it. That's why I keep some. It may look like coffee, but it's actually water here. I've been told by my physician that I'm dehydrated. This is the guy who knows something about water, but he said, you got to drink some more. And so there we go. Drink some more. So, yeah. Okay, so we need to do that. And so how do we do it? Well, there are a number of simple expedients, and these are expedients that people have known for thousands of years work well and in terms of promoting health. And I can list them if you like, because they're actually pretty simple. And these expedients, it's not the same as you go to your doctor and you take this pill and that pill and that pill and et cetera, et cetera. It's just completely different. These are generally ancient mechanisms that have worked well throughout the ages. So, for example, the first one is drink more water, right? That's the no-brainer. And when you drink the water, what happens is that some of the water gets peed out, of course. Other of the water gets converted into easy water. I mentioned earlier that conversion requires some kind of hydrophilic surface, and your cells are filled with proteins, nucleic acids, all of which have mainly hydrophilic surfaces. That's it. And you need infrared energy to do it. And so let me just digress for a moment. Where's the infrared energy coming from? We kind of think of infrared energy. We think of an oven or a toaster. You push down the lever of the toaster, and the coils glow bright orange, and you feel the heat, and you say, "Oh yeah, that's generating infrared energy," and that's correct. But infrared energy is all over the place. It's being radiated not just from your toaster when it's on, even your toaster when it's off to some extent, but it's all over. And the way you can tell that it's all over is actually pretty straightforward. So if you, in the room in which you're sitting, if you turn off all the lights and shut the blinds and make it dark enough that even your smartphone camera can't pick up anything and your eyes can't pick up anything. If you take a sensor that's an infrared sensor, that is, instead of being sensitive to visible light, what cameras do, it's sensitive to infrared, and it's really dark. It picks up a beautiful image. I'd be able to see your glasses and your headphones and the vent that's sitting and the fan that's sitting up above you, et cetera, because they're all generating infrared energy, and that's why the military uses this to see at night, because everything is generating. So if you drink water, you have all this energy from infrared energy coming from outside. And some of the wavelengths of infrared energy penetrate through your body, some rather deeply, and they build easy water. It's not only from outside, but also from inside. All the metabolism that is going on inside your body generates heat. And the heat is almost the same, essentially the same as infrared. The heating is the consequence of infrared energy. So you got infrared from outside and from inside, and therefore the water that you drink, a good fraction of it gets converted into easy water. So that's one expedient. Second expedient, and these are easy expedients, right? And the second one is juicing. So what's juicing? Well, you know about it, I'm sure, but not everybody does. You go into your backyard and you look at the freshly grown plants and you take some of the leaves and you put it in your smasher, which basically squeezes, grinds, whatever, all the juice out of the leaves, and you drink the juice with maybe a little flavoring so that it's palatable. And my late wife used to do that, and I guess I appreciated it. What are you drinking? Well, you're drinking the water from inside the plant cells. And these are freshly grown plant cells full of easy water. So you're essentially drinking easy water and you're bypassing the need for the conversion of the water from liquid water to easy water. So it's an effective way of putting easy water into your body and replenishing what's missing. And that's why many health wellness practitioners advocate this. And, I've heard from some of them that the patient comes and the advice is start juicing. And then they come back a few months later, and not only have they lost weight for whatever reason, but whatever was afflicting them seems to have improved. It's cheap, easy, and quite effective, it seems. So those are two of the expedients. Another one is sunshine. Where I live, unlike where you live in Seattle, in the wintertime, the skies are persistently gray. We don't get much sunshine. The weather is a bit like London, and we see gray skies so frequently. And when the sun comes out, what you see on people's faces are smiles. They're happy. And the usual the usual interpretation is, well, it's a psychological effect. Suddenly we see the light. And and there probably is a certain amount of truth to that. But the other thing is that, the light that's coming from the sun is roughly 50% infrared light. That's why it feels warm. It's not just visible light, it's infrared light. And so the sun is shining, our brain, our head is being exposed to infrared light. Some of the wavelengths don't get through very far, but other wavelengths get through very easily because the evidence for that is you can actually do imaging, brain imaging. You start from a source here, it penetrates, the energy penetrates your skull, goes into your brain, gets scattered, comes back out again and collected, and you get an image of the brain. So it obviously passes through. And that's exactly the energy that's used to build easy water. And I would contend that your default state is almost a childlike state of happiness, right? So so the sun comes and you got a smile on your face because you're building easy water and thereby returning to the default state. So okay, so that's a third one is sunshine, but and a fourth one is, you might say, an amplification of sunshine, a sauna, or as the Finns say, sauna. And I've experienced that myself, both in Finland and then in Russia, where they call it banya instead of sauna, but it's all the same. So what is this? Well, it's a room where there's heat. It could either be dry or moist, but heat, and heat, as we understand, is essentially the same as infrared. So you're exposing yourself to infrared energy, huge amounts of infrared energy, and therefore it's no surprise that if you enter into the sauna and come out 20, 30 minutes later, you feel renewed. You feel happier. Your muscle aches have vanished. You've got new energy. And I would contend that a possible explanation for that is you're simply flooding yourself with infrared energy. And that restores the easy water in your cells. And therefore you feel better because every cell in your body, including the cells in your brain and your muscles and wherever, are now functioning the way they were designed to function, not in the way they were functioning before you entered. Okay, so that's a fourth. Um, a fifth one, maybe the most interesting of all. Well, maybe not. I've got six of them on my agenda. So the fifth one is certain substances, and you're probably aware, and a lot of people are aware that dating back from Ayurvedic times, 5,000 years ago or so, in India, certain substances were known to promote good health. And that's persisted to this day. So many people know, for example, turmeric, that almost no matter what ails you, if you take turmeric, you get better, or at least you move in that direction. And so we became curious about these agents, what's going on. And there are two hypotheses that came up. One is that, well, your body has turmeric receptors in all over the place. And if you hit those receptors with turmeric, you get a positive response, and that particular organ or region or whatever improves. That's one hypothesis. Another hypothesis, there's one effect of turmeric, and that effect somehow is able to pervade the entire body. And obviously the second one is more attractive because it's simpler. And by the concept of Occam's razor, you got two hypotheses. The simpler one is likely to be the correct one. And we thought, well, what is it that distributes itself over the entire body that could be susceptible to the influence of turmeric? And the no-brainer is, well, that's water. It's everywhere, you're right. And so if turmeric has an impact on water, maybe it builds easy water. That would be a simple explanation. That's exactly what we found. We studied exclusion zones in the presence of, by now, 7 or 8 different agents, agents known to promote good health. And it's exactly what we found, that the presence of turmeric expanded the amount of, or increased the amount of easy water over a fairly wide concentration range. That would be relevant to what we might have inside our body. So we studied turmeric for one. We studied basil, so-called holy basil, also from Ayurvedic tradition. And we also studied aspirin. Had the same effect. It's natural. It's from the bark of the willow tree. We even studied Tylenol, which is sort of similar. It's artificial, but essentially very much the same as aspirin. Had the same effect. And the biggest winner of all the bonanza was ghee, clarified butter. And that's been
I'm really into ghee, so I'm happy to hear that.
well, okay, there you go. So we took some ghee, put it in the refrigerator so that it kind of held together, put it in water with microspheres, and looked at the exclusion zone that builds next to it. And it was almost a millimeter in size. You didn't need a microscope or even a magnifying lens to see it. It's huge, has a huge effect. So please continue to enjoy ghee, because it builds exclusion zones like nothing else, or nothing that we've studied.
Wait, is that actually what's so like? I'll make like a hot drink and I'll put ghee in there. This is totally a bracket, but there's like that film that starts on the top of it that I thought was the fat. Is that the fat and also this exclusion zone building?
Well, I'm not sure what it is, but
I guess that's conjecture. But anyway, so the sixth point.
yeah, okay. So, but all of those agents really, I mean, we think the reason that they're good for health is they build exclusion zones in. And the sixth one is connecting yourself to the earth electrically. So what are we? I see your brow is furrowed, so it means you haven't heard so much.
Oh no, it's like grounding.
Yeah,
No, it's grounding. I've heard of it. It's
grounding.
called
Yeah.
grounding. I'm surprised to hear that you've been able to discover that. That's
We didn't discover it.
it's very popular, and I feel better if I walk around. Oh, continue
You
then.
feel better if you walk without shoes and socks um, on
I feel infinitely better. No, I'm almost always barefoot if I can
well,
be,
there you go.
and I just do it because I prefer it. But I have noticed that if I walk around my yard or whatnot without my shoes on, I just my mood gets elevated. That was why my brow was furrowed, because I usually like roll my eyes at people who are of a certain persuasion that are like, "You gotta ground. It's so essential." It seems like it's almost
Well, the question is why. So
right,
why do you
right.
think? Well, I tell you, there are lots of biophysical studies, and there are as many studies as there are theories about why it works. And naturally, I have my own, which is actually rather straightforward. But it has to do with easy buildup. Let me explain. So. Um, I'm not sure if you know, but a lot of people educated in this country have no idea about this, but it's a well-known fact that the Earth is not neutral. The Earth is negatively charged. So I see you're nodding your head, so you know about it. But I got to tell you that 10 years ago or 15 years ago or so, having been educated in electrical engineering to start with, no professor ever told me that when you stick the plug into the receptacle, that third prong is going to negative charge. It was always it's neutral. It's ground. There's no net charge. The Earth doesn't have any net charge. That's ridiculous. Or at least the issue was never even brought up because the assumption was made that it's so. I can tell you that when there was a Russian guy in my laboratory, and just he spent 6 months, and just as he was departing for Russia, we had a kind of final conversation before his flight, and he was telling me about the Earth's electric field. And I said, Andre, you must be talking about the magnetic field. I never heard of an electric field. And he looked astonished. He says, you never heard of the Earth's electric field? You never heard that the ionosphere was positively charged and the Earth was negatively charged? And in between these two, acting like plates of two electrodes or a capacitor, is an electric field? Uh, no, I never heard of such a thing. He said, well, there must be something deficient with the American educational system, which I won't deny. But he said in Russia, even middle school students know that the Earth is negatively charged. And I'm sure that's true. He was not lying to me, but we never heard of such a thing here. So at the end of the day, I went home and I was scratching my head. I couldn't believe what Andre was saying because if it's true, it's consequential. And next morning, one of my students brought me the book of lectures of the famous physicist Richard Feynman, Nobel laureate, who you mentioned, the Einstein of the second half of the previous century. Volume 2, Chapter 9, full of evidence for the negative charge of the Earth. Um, I couldn't believe what I was seeing because if the Earth is negatively charged, it just changes so much. So now, if you think about it, if you connect yourself electrically to the Earth, and the Earth is negatively charged, if you don't have enough negative charge of easy water, negative charge, all your cells are negatively charged. You stick electrodes in. It's been known for more than half a century. We did experiments ourselves early on, numerous people. Um, it's a no-brainer, but if your cell doesn't have enough easy water, it has less negative charge. And so if you connect yourself to an infinite source of negative charge, the negative charge will seep into your body. And we know if you add negative charge to water, we found out experimentally, builds easy water. So I think the simplest explanation for this is when you connect yourself electrically to the earth, you draw some of this negative charge, it rebuilds easy water, and then you function better than you functioned previously. And so that's why if you walk on the grass barefoot, you feel better. It improves, it restores your brain to the default status, which is feeling good. Kids generally feel good. And so this is particularly important these days when everybody is depressed over isolation and over all the afflictions that we're facing on a day-to-day basis. Walking on the grass can really help. I got to tell you just one memory as a kid. I grew up in New York City and Brooklyn, and we had a beach over there, Brighton Beach. And in the summertime, everybody, like almost everybody, was there because it was hot and unpleasant, and you really wanted to be at the beach. And the crowding was such that in order to walk from the boardwalk to the ocean, you couldn't walk a straight line. You had to kind of weave your way between people lying on the beach. It was that crowded. It was almost unpleasantly so. So one day, I think I must have been 10, 12 years old. I was lying there with my friends, and we decided to bury one another just for fun, as kids will do. And I was the last one to be buried. And they buried me up to here. And then, it was late in the afternoon. It was time to go. Parents were waiting for all of us, and they said, "Okay, we got to unbury you because we got to leave." This is one of the most vivid memories I have from my childhood, that I simply did not want to get unburied. The pleasure that I got from being enveloped and electrically connected. It was right near the edge of the water. The sand was damp, and I was very much connected electrically to the earth. I felt bliss. That's the only word I can use to describe it. Bliss was incredible. It was unimaginable. And therefore, I remember the experience to this day because I can't remember any other experience that were as blissful. I hear the same, by the way, from people who do um, transcendental meditation when they meditate as a group, um, and and they do this siddha, siddha, where they actually rise up and come down and rise up. It's a kind of levitation that they do. That's the word they use to describe it when they do it as a group. The bliss is the word that they use, and I remember back from my childhood that particular experience, and so I can imagine exactly what they feel. So yeah. Anyway, connecting yourself to the earth. There are many theories as to why it seems to work as well as it does. It does seem to work, and my own opinion is very simple. It has to do with electrical negative charge that's drawn from the earth into your body, restoring your easy water to the level at which it ought to be.
That's fascinating.
I'm sorry for the long speech, but you asked, so I answered.
No, I've been giving you a lot of broad questions, so I'd imagine long answers. Uh, that's fascinating as far as those six different mechanisms of increasing it. That's really interesting. I similarly to walking on the ground, actually, something that I notice. I've swam my whole life, like mostly competitively. And when I lived in San Diego, I had like a rash of injuries. And I found swimming in the bay for 20 minutes not only like incredibly elevated my mood, but for example, one of the injuries I had was I almost tore my Achilles. I pulled it pretty badly. And coming out of the water, I would notice a large difference in pain and flexibility and being able to walk easier and all of that as opposed to going in. And you're making me look through that through renewed eyes, because like a blissful feeling I had numerous times because the water's freezing cold, and sometimes I'd come out of it with a blissful feeling, and like all the worries in the world went away, and it was just pure connection, and now it's making me think differently to that, which is, I guess, a segue to this. You mentioned in the beginning that electricity is almost an electrical charge, I think is what you said, is an underrated facet of essentially our physical reality,
Yep.
and
Yep.
that it's filling our body and adding more structured water, more positively or negatively charged, adding more negatively charged water in these crystalline structures to our body somehow increasing the functions and kind of bringing everything back to like a baseline homeostasis, like you were mentioning with your mood, which by the way, I'm gonna cite you because I think that's a delightful way of thinking about our base blissful self of, if we like everything is happiness, because I think nowadays we're far too pessimistic. But I guess the lead into the question really is this structured water that is a fundamental part of 95% of the actual fibers and or parts of our body, is it interfacing electricity? Is that what it's doing? Like, what's the mechanism of what it's actually doing with the cells? Is it helping them?
Well, I'm not sure what you mean by interfacing electricity. I'm not sure what you mean by that.
Is it interfacing? Is it the conduit between a muscle tissue and a tendon tissue and a blood, and hemoglobin? Like, what is it doing while it's inside of your body that adding more of it is helping it in some way? Like, what is it fundamentally? What's the mechanism of its action, within the body? Is it helping comprise the structures of muscle
Yeah.
fibers?
Okay. Yeah. Yeah. Let me illustrate. You mentioned muscle. Muscle would be a good illustration. So what happens during contraction? This is unlike the prevailing theory. I apologize for that, but I think the prevailing theory is not adequate by any means. Um, what happens is during contraction is that there's a so-called phase transition. Phase transition sounds very technical, but it's really straightforward. What happens is that the proteins and the water undergo a transition. So when your muscle is not contracting, when it's in the relaxed state, the proteins are long, extended filaments, and the water is easy water. Okay, now your muscle then goes into the frog wants to catch the fly, and so the muscle starts contracting, right, to propel the frog to catch the fly. And and as soon as it starts contracting, what happens is there's a change, so phase transition, a change in the water and in the protein, both. They undergo a change together. The water undergoes a change from the easy water to ordinary water. And and the proteins undergo a contraction themselves. You won't read about that in the textbook, but if you read my book on muscle contraction from um, 1990, you'll see the evidence for that, and there's a lot of evidence. So your muscle contracts, the proteins fold or contract, and the water undergoes a change. And then when the muscle is ready to relax again, it undergoes a transition back to the original. The water becomes structured, and the proteins unfold back to their original state. And by the way, that's the stage that requires energy to get back to that state. You need energy to build the easy water, the structured water, and you need energy to return the proteins back to their state. And if you don't have enough, you've had the experience. Your after three matches of tennis, your muscles have had it, and they may be unable to return to their initial state, and you get a knot
Or
in
a
your muscle,
cramp? Yeah.
right? And that's just an example of it. So the process of contraction involves both the proteins in the cell and the water in the cell. And so if you can't restore the full amount of easy water, you can't get back to it, your muscle is not going to be ready for the next contraction. And your muscle is going to be dysfunctional because the water is essential for the contractile process. It's not irrelevant at all. It's central. And so you got to make sure that by hook or by crook, that you maintain a full and complete complement of easy water. And um, I guess that's how I would answer your question, although I may have deviated from the exact. Yeah.
No, no, no. That makes complete
Okay.
sense. That makes complete sense. So just to make sure I get it, the muscle is at rest, and like I'm about to swing a racket. The ball is coming towards me. I'm waiting for the right time, and now I'm starting to swing the racket. From the moment it's at rest, it's easy water,
Right.
And then when the muscle is contracted, the proteins are flipping it, which is the contraction of the muscle to give it the force and the energy to put that weight, or well, it's weight because we see it measured as weight, but it's really that force into hitting the ball. It hits the ball, and I'm going through my follow through, and I'm relaxing the muscle, and then it's taking energy, from calories or whatnot. It's taking it from and flipping it back to easy water. So
Precisely.
it's easy water at rest, and then and what actually is contracting and creating the force, the energy of force, is flipping it back into H2O from H3 2
H3O2.
or H3O2.
Yeah.
And
Yeah. I
yeah,
mean,
yeah.
yeah, I wouldn't
So
say
it's
that's
flipping it.
creating
It's
the
so
force, but it's part of the process. It's central to what goes on when your muscle
okay.
contracts. Yeah, absolutely. And if I may interject something um, about the energy inside your body, we've all learned, and we know if we eat pizza, we get energy. Or no matter what we eat, we get energy from it. And there's not much dispute. And how does it work exactly? So we all learned that the ultimate source of energy in your body is from ATP, adenosine triphosphate. And the story is that we've learned, and we've known now for 70 years, or even more, is that the food that we eat gets converted through a very complex biochemical process into ATP, and ATP has a so-called high energy bond. And that high energy bond is ultimately where the energy lies. And um, it's in every textbook, and we learn it, and we just presume it's true. Uh, However, if you, it might not be true. And let me just give you the background of this, and tell you where else the energy might come from. Um, so there was a well-known group, academic group in chemistry, that came up with this idea that ATP has a special high energy bond, whose energy can be released to contract your muscle or do whatever. A year later, another group reported that the first group is wrong, that they made a simple arithmetic mistake. And this is described in the website of Gilbert Ling, whose name I mentioned. It's gilbertling.org, where he discusses the situation. And nobody has ever, to anybody's knowledge, or to his knowledge and my knowledge, ever followed up. So if this group that challenges the result is correct, it may mean that this mechanism that is in our books, and we all learn it, it's fundamental, might not be right. Um, and I don't know the answer. I don't know if the original group was right or the challenger was right, but nobody's ever followed up, so it's not clear. There's another potential source of energy, um, and the extent to which it really works is not clear at all, and that is the electrical energy that I talked about, right? So the water that's in our cell, uh, the water is the easy water is negatively charged, and so you got a cell that's full of this negatively charged water, and that, by the way, I would say parenthetically, is why our cells bear net negative charges, the water. And if you read in the textbook, you'll find that it has to do with membrane features like pumps and channels. And I wrote a paper a few years ago to dispute that, and I won't go into the reasons why, but a simpler explanation is easy water has negative charge. Therefore, if your cell is filled with easy water, it's got negative charge. And by the way, if your cell is pathological, it has less negative charge. That's been demonstrated because one of the reasons for the pathology is the lack of easy water. So that um, at any rate, it is possible that some of the energy that our body needs to do what it's doing comes from that electrical charge. All those negative charges inside the cell want to get away from each other, just in the same way that in the atomic nucleus, as described, all those positive charges want to get away from each other. And that amounts to potential energy. Right. So your cell is filled with potential energy because of this negative charge from the easy water, right? And the question is, to what extent is that potential energy used by your body? It might be zero, but it might be a lot, you see. And when your cell is activated, if this negatively charged EZ water transitions into ordinary water with no charge, that energy is actually used. And so the question is, to what extent you, me, and everybody else, to what extent does our energy come from electrical charge as opposed to ATP? The answer is unknown. It could be zero, it could be 1%, it could be 100%. It's not really clear. And so this is a frontier issue that, in in my view, it needs to be seriously addressed because you want to know where your energy comes from. And I just you're about to ask a question, but let me just finish by mentioning, there are people who don't eat. Um, there are many of these, and a lot of people believe that it's impossible. How could you survive without eating? And um, but this is so well documented now that it's really hard. It's hard to deny the fact. There's even a film where a couple of dozen of these people are interviewed. The producer is a guy named Straubinger from Austria, and I think it's called "In the Beginning There Was Light." And he says that light, the energy is coming from light. So if these people don't eat, then the transition. Um, I mean, there's no food that they can convert into ATP, and the question is, well, where do they get their energy? I know some dancers who dance every day, or one at least, who contacted me, and she says that she she'll spend 2, 3, 4 weeks without eating. She just has no desire, and yet she dances every day. And, it's just incredible because what energy is required for that. And so it is possible, in fact, that some energy comes from the electrical charge that I've been talking about, which in turn comes from the sun, which comes from light. Uh, I mean, essentially. So plants get all their energy from light, and you and I may get at least some of our energy from light in the same way as plants do. So the first step of photosynthesis, in fact, is the splitting of water into H plus and OH minus. It's the same
Hmm.
as what we discovered more generally, that the splitting of water into the negative and into the positive. There may be a correspondence then between what we discovered and the first step of photosynthesis. It may be that what we discovered is a kind of generic photosynthesis that we as animals use the same way that plants use it. Something to
That's
think about.
fascinating. Have you ever heard of Joffrey West? He's like with the Santa Fe Institute. He's a physicist at
Joffrey, what?
Joffrey West, West.
I'm afraid not.
He's okay. Well, he's a physicist. He's a physicist with the Santa Fe Institute. He wrote a book that I'm still digesting before reading a second time called Scale, and it's about the science of scaling. And something that I was wondering when I was reading through some of your work is actually right where you're at, which is without more science that's necessary into it. But one of the things that Joffrey West brings up is there's these somewhat golden numbers that appear in nature that are all scale and power laws. And one of them that's fascinating to me that I use to try to spark people's curiosity when I meet them on the street of physics is there's certain numbers that reoccur. And one of them, I think it's 1 to the 4th. I'm not exactly positive. But
Sorry,
it's
1 to the 4th?
I believe, I'm not sure. It's 1 to a fractional exponent. And what it does is it's the energy necessary for the size of an organism. So like the example that he uses is a mouse versus a blue whale. And the energy
Yeah.
required, per the size of the organism goes down with the larger the organism is. So the larger you are, in essence, the less you need to eat. Which one of the things I was wondering from your work is I wonder if the larger the size means the more structured water to keep that system in place, right? So I wonder if some of the potential energy is somehow derived from the size of it, which is why essentially, something that's double in size needs only 2/3 around the amount of energy as opposed to needing double the amount. You would imagine, you scale an organism up double, its requirements are double. And it's actually not. It goes down. It's like about 75% around, right? Which is fascinating, and it's an area that I'm eagerly waiting more people to get funding to find out some of these biological processes, because that's fascinating.
Um, I I'd not I'd heard something about this, but not in any detail, and I have no comment. I don't. I don't know. I can imagine though that if much of your energy comes from metabolism, heat that is generated, that it might be more efficient for larger animals than smaller animals because the infrared energy might dissipate into the environment for the smaller ones, but the bigger ones, no. It has to go through all that tissue in order to do so. So it could be more efficiently consumed by the larger animals. That would be my first thought, but obviously it needs thinking. I don't have I don't have an
Yeah.
answer to it.
It's a new angle to the same thing is really what it is. I wasn't expecting you would have an answer to that. It's
Well,
more just like
it's
another aspect
yeah, no,
of nature
I
that,
don't.
yeah. Um
But it's certainly interesting. Yeah, yeah.
yeah, it's interesting. So closing on this then, is some of the health positives that come out of structured water, or having these type of substances, for example, that like turmeric that you mentioned, that increase the amount of structured water or somehow aid that mechanism of going across. Which sauna, by the way, that's amazing. I'm actually really well read on saunas as a health benefit, and it being assisting in structured water is fascinating. That's very interesting. Um, if you were to take water that is in some way more, has a higher concentration of structured water in it, perhaps it's been bathing in sunlight or something like that, are the health benefits from that just because it's very similar in the way of the other things? Is it just aids and assists, and has people been able to start seeing markers of what some of those benefits are as far as overall health or certain conditions that it can assist in, or is this another area that's kind of starting?
Yeah, yeah. Um, yeah. So particularly in agriculture, dealing with the health of plants, there are many reports. People have been studying this. Some of it is not published. Some of it is more anecdotal. But people have been using various kinds of structured, so-called structured, easy, whatever water, in agriculture, and they find that it really works, and that the plants are more robust, more healthy. They grow larger. In human health as well. And so that may be where we started this interview with the point that some people say, well, structured water is just a big marketing scheme, um, you know, and I could see how one can surmise that, because some of the companies, some of the various water producing companies, and there are so many of them now, some of them have really taken up the idea of structured water, easy water, fourth phase water, and they tout that as being that their water contains more than other waters, and I can see how that can be interpreted as a marketing scheme. We don't have anything to do with that. They have just taken up the idea, and there should be something to it, because if real, the companies who produce that kind of water, they don't generally describe their evidence that they actually that their water contains easy or structured water. There are actually fairly simple ways of determining how much easy water there is in a given sample, but they don't do that in general. So it's really difficult to, in many cases, difficult to know exactly how much easy water, what fraction of the water is easy water. It's never that we know of 100%, except except when you so-called dehydrate the water. It seems like a strange word, but you're left with a kind of powder, and that powder is pure EZ. We've been studying that. It was actually discovered by an Italian group headed by Vittorio Elia from Naples. They published a few papers showing that they can produce so-called dehydrated water. If you can imagine such a thing. And they gave us a sample of it, and I was hoping that people in my lab would test it, but we've now reproduced this, and we've demonstrated that this is not due to some sort of contaminant or something that might be in the water. It's really easy water, and we're working on preparing a manuscript for it. So yeah, this stuff seems to be good for health. In theory, it should be good for health. It's been demonstrated in various studies on plants that it really works. Plants prefer rainwater to artificial hydration. The plants grow bigger and healthier when you get rainwater. And one of the reasons for that, I think, is that a raindrop consists of an easy shell and ordinary water inside with protons. And so it's got an easy component to it. And the plants like that easy, and therefore they grow better. So I'm sorry I can't give you definitive response to your question, but it looks promising, and also sometimes the spring waters, which come from some of which come from fairly deep within the earth, many of them appear to have a lot of easy water, because I've seen tests of some of them, and the tests indeed show positivity. So drinking spring water, some spring waters, not necessarily all, appear to be good for health. So there we have it.
That's fascinating. No, I mean that's sparking the curiosity to at least look for it more in the future. That's fascinating. This is such a earth-shattering, mind-blowing, mind fuck of a subject, and I think that's the only way to properly emphasize it, to be honest, because of how much this is scratching the surface of what is potentially possible, or what it may require asterisks of going around through everything of, how our body functions, to how plants absorb, how to have good health, what is, baseline. It is, your work is fascinating. I'm so glad you're out there. I'm so glad that you're doing this. I'm so glad you took the time to talk with me.
Well, thank you. Thank you for your kind comments. I appreciate that. Um, yeah, for me, it's really exciting. You asked early on what gives me pleasure, and it's a discovery that you discover something, and if it's real, it generally there's wide application, and it serves to answer questions that have existed beneath the surface that people don't really pay attention to, and that's ultimately what, for me, gives me great pleasure. And so I appreciate your enthusiasm. That helps. you know. Um,
Yeah,
Thank you.
it's fascinating.
Yeah.
Yeah, no problem. I have this truism that I quite like philosophy, and the truism is that I think the truth only lies in paradox. Things that are paradoxical tend to be closer to reality or truth. I think often reality and truth get misconflated, but they're almost at the base level should be the same.
Hmm.
I think our own personal experience is what gets layered on top of that and colors our view of the world. If it's, this is upsetting the status quo, we shouldn't be looking into this. It's so foundationally wrong, we can't think of it. Or it's, no, this is weird and funky and doesn't seem to be, but it is, and this is the way that it's changing things. We may have to think about the difference between the lines we draw, and maybe think of a different way forward, which is the space that I like to live in. So your work is it's going to give me a lot to look into for years to come, and I appreciate it.
Well, thank you. Have a read of if you haven't read it all, the fourth phase of water. It's a really popular.
It's in the mail. It's in the mail right now,
Oh,
actually.
okay, that's great. Yeah, um, I try, in simple concepts and simple words to describe all the phenomena that we've barely touched on, and there are many details there and explanations for phenomena that we just ignore, but we need to understand. And in the book, I provide what I believe is a simple explanation for all that. Hope you enjoy it.
Yeah, and I'm looking forward to it. And simple is genius, so I appreciate that. And there's a lot more to this. I mean, like there's so much. This is a boundless subject that. I mean, the information, like capabilities or information in water and all of that, like that I found. I mean, I'm in, emerging technology is the space I live. Emerging information technology, because I would unbelievably underscore that there's no new revolution happened even. I won't go into it. It's for another diatribe. But what we mostly think of revolution as far as communication technology is building over things that are very old. We're just able to have Moore's law that saves us to actually give us some type of positive change. We're just running off of being able to make things smaller and smaller.
Yeah. I'm with you on that. Yeah, I can see that philosophically speaking, we're on the same wavelength.
Yeah. Well, we can stop the
Absolutely.
recording there. Thank you again. Is there anything else you
Um,
could say before we can wrap in a second? But I'll stop the recording unless there's anything else you want to say.
Okay, well, thank you. Thank you for your great questions, and
Yeah.
thanks for the opportunity. I appreciate it.
Thank you very much. If you like what you hear, please tap that follow or subscribe button. You also can find this episode, all episodes in the series, or check out our Daily Minute podcast by visiting us at bandwidth.productions.